Okay, the topic of this video is orbital mechanics, and that's the rest of gravitation. So far, we've looked just at the force of gravity between big objects in space, as well as acceleration due to gravity. Now we're actually going to look, and those are important, but now we're actually going to look at how orbits work and some neat features of it. When I teach this class in person, I usually refer to this as kind of like baby astrophysics. Which is one of my favorite parts of physics, and that's why I get so excited to teach this. So first thing we're going to look at in orbital mechanics is orbital speeds. Now, very obviously, this simply means the speed of an object in orbit. And orbit just means that something is going around something else. And this is often, but not always, in a circular fashion. And we like when it's in a circular fashion because when this happens, that means that we can use the idea, if something is moving in a circle, we know there must be a centripetal force on that object. So, our first example, low Earth orbit. This is a real thing. Low Earth orbit is a possible orbit around Earth that allows satellites to move around Earth without falling down. So in other words, that's how they stay up there. LEO, that's the abbreviation, LEO's upper maximum is 2 million meters above Earth's surface. If Earth's radius is 6.37 times 10 to the 6th meters, and its mass is 5.97 times 10 to the 24th kilograms, how fast must a 200 kilogram satellite move in order to stay at this orbit, and what will the orbital period be? So, like last time with the acceleration due to gravity, we could do 2 or 3 calculations in order to figure this out. But wouldn't it be nice if there's just one equation that we could derive very quickly at the beginning of the problem, and then therefore use and know that that's the equation for orbital speed? We're going to try and find one. So it's going to take us some prep work right now, but we're going to try and find one of these. So let's see here. We know that this object is in... so let's see, how are we going to start this? We know this object is moving in a circular orbit, and we know that the reason it's moving in a circular orbit because the force of gravity keeps the object bound to the Earth. So since gravity is what causes the circular motion, gravity points in towards the center of that circle, the satellite is attracted to Earth, we can say that Fg is equal to Fc here. Now that's interesting. We know other equations for both of these. We know that Fg is equal to g little m, big M, little m being satellite, big M being Earth in this case, over r squared, r being the distance between the satellite and the Earth, the center of the satellite and the center of Earth. We know that Fc is equal to mac, which is equal to mv squared over r. M being the satellite mass, the mass of the thing that's moving in a circle, v being the speed of the thing moving in a circle, and r being the radius of the orbit, of the circle that it's tracing out. That's the same, if you think about it, this r, well, we know these masses are the same, so let's get rid of those. But you know that these r's are the same, okay? I am ignoring this middle part, by the way, because it was just an intermediate step. We know that this r, the radius of the circle that the satellite is tracing out, it has to be the same as the distance between the satellite and the center of the Earth. Now that's not always going to be the case, but it's definitely the case here. So these r's actually mean the same thing. So if I cross one of them out, r gets canceled out over here, and this just becomes r. I now have v squared equals g times big M over r. What this becomes is v equals the square root of g, m, and r. So what does this mean? The orbital speed that something orbits at is dependent on only 2 things. The mass of the body on that it's orbiting, and this is for objects that orbit because of gravity, the mass of the object that it's orbiting, and how far away it is from that object. Very, very interesting. So we can do some work. The only thing we have to worry about right here is how far away, what is this radius? And this is a little tricky because you might say, oh, it's 2 million meters. Careful, it's 2 million meters above Earth's surface. Earth's radius is below that, and we know the radius of this circle goes from the satellite to the center of the Earth. So we have to take into account not only Earth's radius, but also the distance above the surface, the extra distance above the surface that the satellite is orbiting at. So what we need to do is figure out the actual r. So I'm going to write it like this. R must be equal to the radius of the Earth plus the height of low Earth orbit. Radius of the Earth is 6.37 times 10 to the 6 meters. Radius of low Earth orbit, or not the radius, but the size of it, it's 2 million meters farther up. 2 million is 2 times 10 to the 6th meters. So this must be 8.37 times 10 to the 6th meters. Okay. So we can plug this in. We have V equals the square root of 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared. I know I'm writing really small because there's something else I want to do here. The mass is, let's see, 5.97 times 10 to the 24th kilograms. And the distance, notice it is not squared, is 8, or the radius I should say, 8.37 times 10 to the 6th meters. We type all that in. We make sure that we don't forget the square root because that is a very bad mistake to make, that lots of people will make. And we see that this satellite, any satellite, it doesn't even depend on the satellite's mass, that canceled out. Any satellite must be moving, and in low Earth orbit at this height above Earth's surface, must be moving a shade under 6,900 meters per second. If you think about it, that's about almost 7 kilometers per second. That's like going from Clayville to Chadwick's in, 1 second. That's how fast this has to be moving. Very, very impressive. We are also asked what the orbital period is. Now that we know the speed, that's very easy. We know V equals d over t. We know the time would be the orbital period, that's capital T. We know the speed, and if the orbital period is the time it takes to orbit once, the distance it travels while orbiting once is just the circumference of a circle. So we have V equals 2 pi r over t, which means that t must be equal to 2 pi r over v. 2 pi times 8.37 times 10 to the 6th meters divided by the orbital speed of 6,897 meters per second. 2 times pi times 8.37 E6 divided by 6,897 gives us approximately 7,625 seconds. Or, if you were to convert that to hours, it's a little bit over 2 hours. So that's how long a satellite in low Earth orbit takes to orbit the Earth. That's crazy. That's 2 hours to orbit the Earth. That's extremely fast. Okay, let's do the next one. Again, notice that the satellite's mass, the mass of the thing in orbit, did not matter. I'm just going to write that here. Mass of orbiting body cancels out. Okay. All right, second question. Given the sun's mass as 2 times 10 to the 30th kilograms, Venus mass as 4.87 times 10 to the 24th kilograms, and the average Venus-Sun distance as 1.08 times 10 to the 11th meters, with what speed does Venus revolve around the sun? How long does it take Venus to revolve around the sun? So, we're going to start off the same way we did. We know we can derive the orbital speed by realizing that the force of gravity is equal to the centripetal force here, which is equal to MAC. Force of gravity is G little m big M over R squared, which equals mv squared over R. The little m's cancel out. These R's are the same. In this case, with a circular orbit, the radius of the orbit is the same as the distance between one of the orbiting, the same as the distance between the centers of the orbiting body and the body it's orbiting around. So one of these R's will cancel out. We take the square root of both sides. We end up with V equals square root GM over R. And that would be the square root of 6.67 times 10 to the negative 11th newtons times meters squared over kilograms squared. Which mass do we use? We use the mass of the big object, the object in the center of the orbit, or the object being orbited. That's the sun's mass. That's 2 times 10 to the 30th kilograms. And the distance between the Sun and Venus is 1.08 times 10 to the 11th meters. And we see that the Venus, the second planet from the Sun, orbits with an orbital speed of just over 35,000 meters per second. Very, very, very fast. Like something moving from Sequoia to Rome, New York, in 1 second. That's extremely fast. Notice we could have done, and you can find this without going through this equation. This is much quicker. Otherwise, you'd have to use like 2 or 3 different equations. Once again, if we want how long does it take Venus to revolve around the Sun, we're looking for, that's a question of speed. So we're solving for the period. That means we must do like we did before. Since the period is how long it takes to go around once, we need the circumference divided by the speed. And once again, that's 2 pi times 1.08 times 10 to the 11th meters divided by 35,145 meters per second. And what we get is an answer of approximately 1.93 times 10 to the 7th seconds. And this comes out to approximately 223.5 days is the orbital period of Venus. And you can do that conversion yourself, you can look it up, you'll see the same thing. Okay. We're going to move on now. We're going to talk a little bit about orbital energy. Orbital speeds are great. We use that to talk about orbital energy because that's honestly even more important. Let me kind of outline that. I just want to make one point. When we talk about orbital energy, we're talking about kinetic and potential energies. And when we have a bound orbit, when we have something that is in orbit around something else, and there's no chance of it, moving off unless something drastic changes. So in a bound orbit, ET is always negative. So the quick way to tell if something is in a bound orbit or not is the total energy negative? If it is, then we have a bound orbit. If it's not, then that object might be near something right now, but it's not bound to it. It will eventually move on and leave that area of influence. It'll leave that object behind. It's not bound to it. It won't stay in orbit around it. It'll go flying off. Okay, so let's look at Earth. Really easy case. If Earth's mass is 5.97 times 10 to the 24th kilograms, the Sun's mass is 2 times 10 to the 30th kilograms, and the Earth-Sun distance is 1.5 times 10 to the 11th meters, calculate the gravitational potential energy of the Earth-Sun system. Remember, we're not using MGH here. We are using instead the fancy version of the gravitational potential energy equation. That would be negative G M big M over R. Negative because we want, because the negative shows us the bound property. Over R means that we set at an infinite distance, there is no gravitational potential energy. So let's plug our numbers in. The calculation is very straightforward. 6.67 times 10 to the negative 11th newtons meters squared kilograms squared. Mass of the Earth, 5.97 times 10 to the 24th kilograms. Mass of the Sun, 2 times 10 to the 30th kilograms. And the average distance between them is 1.5 times 10 to the 11th meters. When we plug all this in, let me do that again. There we go. Times 5.97 E24 times, wasting my own time. I'll just make the next one negative. Okay. I'm having a rough day with this one. Nope, okay. We're just starting over. How many more times do you think it's going to take me to do this correctly? This must be fun for you guys to watch. There we go. There's an answer, I believe. The gravitational potential energy is negative 5.3 times 10 to the 33rd joules. Now, calculate the kinetic energy of the Earth. We know kinetic energy is given by 1/2 mv squared. And interestingly, and again, normally I would derive this whole thing from scratch, but I'm not going to here. We just found the speed Earth goes around the sun, so let's see, we want the orbital speed of the Earth. That's given by square root of gm over r. So this is really 1/2 times m times the square root of gm over r squared. Squaring something under a square root just makes the square root go away. This becomes 1/2 gm over r. Now that might look kind of interesting to you because that's very similar to the equation above, and we'll talk about that in a second. If I plug all these in, I end up with a kinetic energy of 2.65 times 10 to the 33rd joules. And we'll talk about why that's important in just a second when we go and talk about the total energy and why this result is very, very interesting.